In the last video, we were given a multivariable function and asked to find and classify all of its critical points. So critical points just means finding where the gradient is equal to 0. And we found 4 different points for that. I have them down here. They were 0, 0, 0, negative 2, square root of 3 and 1, and negative square root of 3 and 1. So then, the next step is to classify those. And that requires the second partial derivative test. So what I'm going to go ahead and do is copy down the partial derivatives, since we already computed those. Copy. And then just kind of paste them down here, where we can start to use them for the second partial derivatives. So let me clean things up a little bit, and we don't need this simplification of it. So we've got our partial derivatives. Now, since we know we want to apply the second partial derivative test, we've got to first just compute all of the different second partial derivatives of our function. That's just kind of the first thing to do. So let's go ahead and do it. The second partial derivative of the function with respect to x twice in a row, we'll take the partial derivative with respect to x and then do it with respect to x again. So this first term looks like 6 times a variable times a constant. So it'll just be 6 times that constant. And then the second term, the derivative of negative 6x, is just negative 6. Moving right along, when we do the second partial derivative with respect to y twice in a row, we take the partial derivative with respect to y and then do it again. So this x squared term looks like nothing, looks like a constant as far as y is concerned, so we ignore it. The derivative of negative 3y squared is negative 6 times y, and then the derivative of negative 6y is just negative 6. And then we can't forget that last, crucially important, mixed partial derivative term, which is the partial derivative of f, where first we do it with respect to x, and then with respect to y. The order doesn't really matter in this case, since it's a perfectly ordinary polynomial function. So we could do it either way, but I'm just going to choose to take a look at this guy and differentiate it with respect to y. So the derivative of the first term with respect to y is 6x. And then that second term looks like a constant with respect to y. So that's all we have. So now what we're going to do is plug in each of the critical points to the special second partial derivative test expression. And to remind you of what that is, that expression is, we take the second partial derivative with respect to x twice, and I'll just write it with a kind of shorter notation using subscripts. And we multiply that by the second partial derivative with respect to x, and then we subtract off the mixed partial derivative term squared. So let's go ahead and do that for each of our points. So when we do this at the point 0, 0, 0, 0, what we end up getting, plugging that into the partial derivative with respect to x twice, 6 times 0 is 0, so there's just negative 6. So that gives us negative 6 multiplied by, when we plug it into this partial derivative with respect to y squared, again, that y goes to 0, so we're left with just negative 6. And then we subtract off the mixed partial derivative term, which in this case is 0, because when we plug in x equals 0, we get 0. So we're subtracting off 0 squared. And that entire thing equals negative 6 times negative 6 is 36. 36. And we'll get to analyzing what it means that that's positive in just a moment, but let's just kind of get all of them on the board so we can kind of start doing this with all of them. If we do this with 0 and negative 2, 0 and negative 2, then once we plug in y equals negative 2 to this expression, this time I'll write it out, 6 times negative 2 minus 6, so that's negative 12 minus 6, we'll get negative 18, negative 18. Then when we plug it into the partial derivative of f with respect to y squared, again I'll kind of write it out, we have negative 6 times y is equal to negative 2 minus 6, so now we have negative 6 times negative 2, so that's positive 12 minus 6. So that will be a positive 6 that we plug in here. And then for the mixed partial derivative, again, x is equal to 0. So the mixed partial derivative is just going to look like 0 when we do this. So we're subtracting off 0 squared, and we get negative 18 times 6. And geez, what's 18 times 6? So that's going to be 36 times 3. So that's the same as 90 plus 18. So I think that's 108. Negative 108. And the specific sign, the specific magnitude won't matter. It's going to be the sign that's important, and this is definitely negative. So now, kind of moving right along, these examples can take quite a while. If we plug in square root of 3, 1, square root of 3, 1, what we get. Now instead of plugging in y equals -2, we're plugging in y equals 1, so that'll be 6 times 1 minus 6, so the whole thing is just 0. And then for the partial derivative with respect to y squared, instead of plugging in -2, now we're plugging in y equals 1, so we have -6 times 1 minus 6, so the whole thing is -12, so -12. And now for the mixed partial derivative term, which is 6x, x is equal to the square root of 3, so now we're subtracting off the square root of 3 squared. So what that equals is, this first part is just entirely 0, and we're subtracting off 3, so that's -3. And then we have square root of 3. No, we don't. That's what we just did. Now we have negative square root of 3, 1. And this will be very similar because this first term just had a y and we plugged in the y, so it's also going to be 0 for totally the same reasons. And same deal over here, the value of y didn't change, so that's also going to be -12. It doesn't really matter because we're multiplying it by a 0, right? And then over here, now we're plugging in negative square root of 3, and that's going to have the same square. So again, we're just subtracting off 3. So what does this second partial derivative test tell us? Once we express this term, if it's greater than 0, we have a max or a min. That's what the test tells us. And then if it's less than 0, we have a saddle point. So in this case, the only term that's greater than 0 is this first one. And to analyze whether it's a maximum or a minimum, notice that the partial derivative with respect to x twice in a row or with respect to y twice in a row was negative, which indicates a sort of negative concavity, meaning this corresponds to a maximum. So this guy corresponds to a local maximum. Now all of the other three gave us negative numbers, so all of these other three give us saddle points. Saddle points. So the answer to the question, the original find and classify, such and such points, is that we found 4 different critical points. Let's see. 4 different critical points, 0, 0, 0, -2, square root of 3, 1, and negative square root of 3, 1. And all of them are saddle points except for 0, 0, which is a local maximum. And all of that is something that we can tell without even looking at the graph of the function. And with that, I will see you next video.